Welcome to our next module where we're going to be talking about the network layer. And we start in this part one about just basic introduction about the network layer itself and router structure. So as a reminder, so network layer business is about source, destinations, and delivering packets between the source and destination. So we're dealing with packets that received from the transport layer being delivered to network layer. A network layer decides what to do with the packet, effectively encapsulates this packet into the network layer header, decides what to forward, and gives it to the link layer to forward further. And on the way back, and in destination, you basically get the packet, decide that this packet is destined to the host, decapsulates and gives it to transport layer. So that's kind of two parts, two endpoints of the network layer protocol. In addition to that, each router can be considered as a kind of intermediary destination. And effectively, it's also receiving the packet, it decapsulates, but instead of delivering to the transport layer, it's simply making a decision where to forward. And we're going to be talking more extensively how exactly this forwarding process is working. And one thing that I would like to note is that kind of this network layer protocol is the one that is have to be common among all the routers and all hosts in the network. Other protocols, okay, maybe with the exception of transport layer protocols, that needs to be run on the end host. One of the core ideas of IP-based networking protocols is that it operates on the concept of subnetworks, or subnets in short. And basically what happens is the subnets is some kind of an abstraction that connects the networks. You can think of subnets as something equivalent of Ethernet segment, but it's not exactly the same, because you can have on the same Ethernet segment you can have multiple IP subnetworks. And we'll try to look a little bit further when we're going to be talking about routing tables, because the routing tables basically defines what subnet is and how you deal with the subnets. So as part of the IP protocol, it basically provides two basic functions. One, it assigns global unique addresses. So kind of one of the requirements is all hosts on the network, hosts, routers, and everything have a unique IP address. So, and this IP address is globally unique for the whole IP network, and our IP network is internet, so it's globally unique. And finally, it's trying to deliver datagrams from the host and destinations. And as you already noticed in the project too, the delivery is not guaranteed. So some of the packets are being lost, some of them are being delivered. IP addresses, as I said, it's a globally unique identifiers, so therefore there has to be some way to allocate or to manage those IP addresses. And what exactly is happening? This is we have a currently tiered structure where there's a standardization body, in this case is IETF, defines standards for the networking protocol. So we have IPv4, IPv6. And the standardization body designated IANA, a special organization, to allocate basically IP addresses to whoever needs them. But IANA directly not talking to the customer, so you cannot as a user or ISP go to IANA and ask for the IP addresses, but rather IANA delegates this function to regional registry, so regional internet registry, or RIRs, and there are several of them for different continents. They actually work with ISPs, so they have ISPs have some relationship with the RIR, with a specific RIR, and if they need some IP address blocks that they need to be globally unique, they simply go to this RIR, request, kind of submit some kind of a form, and pay potentially some amount of money as a membership, and they get the allocation if some addresses are available. And I'm going to be talking about this a little bit later. And finally, as users, we technically don't go to RIRs, so RIRs deals with ISPs specifically, but we also get our IP addresses, but as part of the so-called the sub-allocations from the ISPs. And this is just a highlight of several RIRs that exist in the world. So effectively we have 5 for North America, for Latin America, for Europe, for Africa, and for Asia Pacific region. Getting back to the network layer protocol, so the key functions of the networking layer is, as we already discussed, is to deliver packets towards the destination. And how it's been accomplished is basically through forwarding and routing. Forwarding is basically the actual process of determining, like given the packet arrives to the host and like a router, what to do with this packet, like which interface to deliver or deliver to the transport layer protocol. And routing is some form of creating a guidance for the forwarding. It will be done in the form of routing or forwarding tables, and those routing or forwarding tables are being populated either manually or some automatically or through routing protocols. But we're going to be talking more extensively in the next part. What I want to talk now is basically the forwarding structure, like how the forwarding can be accomplished, because there's multiple ways you can implement forwarding, and how exactly it's done, it really depends on available hardware or like some algorithmic logic. So on a high level, like each router would have these two components. Basically, we're going to have a routing or management plane, and we have a forwarding plane, or a control plane and data plane. And basically, we're going to also, for the forwarding plane, we're going to have input ports and output ports, and for the control plane is some form of a routing processor. It's something that will decide how to construct the routing tables and somehow deliver them either to the switching fabric or to the ports, or there's various combinations of these. This is an abstract picture of basically any router, and there's a lot of complexities or a lot of options that exist in different parts of this picture. So for example, in input ports, so we basically have some form of line termination, basically the outlet that we need to connect a cable, or if it's Wi-Fi, some form of antenna. We're going to have some form of a link layer protocol. So in order to decode the signal and do some initial pre-processing, either in hardware or hardware software. And finally, we may have either lookup and forwarding embedded as part of the port. So the port may decide where to forward and kind of decide and deliver to the switching fabric for the further delivery. Or this decision can be offloaded to the CPU, and then the CPU will be able to decide where to forward. But one element that probably exists in most of the implementations is at least queuing, because you may need to do some kind of a queuing on input part. And talking about the switching fabrics, there's again a wide variety of implementations. I just want to highlight the complexity of this, how it can be accomplished. It's either accomplished using the memory, kind of main memory with the CPU, either some form of a buses, like either one bus or some kind of routing fabric. So the last two is basically more applicable for hardware routers, but just remember that they exist, these structures exist in the universe. So the simplest part is the CPU based. So this one, even though it's called the first generation router on the slide, this is basically how the software routers operate. We receive the packet, we get this packet to the main memory, we decide what to do with this packet, and we forward this packet outside to the port we have determined. This basically will be limited by the bandwidth, kind of memory bandwidth, like on how much CPU we can spend, and so forth. So real routers, like the real big routers, are not really implemented in this way. They're trying to do a little bit more optimal things. And what the big routers are trying to do, they're trying to move most of the logic of how to forward the packet into the ports themselves. So basically, if we're talking about the input ports, so we receive the packet, we kind of decode the packet from the link layer, then we have some form of a CPU or some processing to decide which output port needs to be used to forward this packet. How exactly it's been decided, it's basically we still need the control plane to kind of put some information in each CPU, or there's some form of lookup in existence. But in any case, just remember, the decision can be made, and in the current routers, it's being made in individual ports, and then packet being forwarded to the outside port, and that's it. So this one is much more efficient because we don't go to a single CPU and deciding and kind of going back to the same memory bus. But there's still inefficiency in terms of the whole bandwidth of the router is dependent on the speed of the single bus, because each packet has to go to the bus in order to be forwarded outside. So there's a few more optimizations. So what they're trying to do is use some form of a networking, like to connect the input and output ports. And in this, the logically, it's basically the same bus. It's just you will be able to address the output port a little bit more efficiently, with not just putting on the same bus, but rather having multiple buses in existence, so you can send packet a little bit more directly. There are many implementations, and this one is just to highlight that these mechanisms exist. Now I just want to get a little bit ideas about the queuing part as for the input and output ports. In one of the first modules, I was talking about the queuing, so that we have to calculate the queuing delay. The queuing delay is actually a little bit more complex than just queuing, like for waiting for something, because queuing can happen at input. And it can happen in input if the switching fabric is a bit slower than we receive in the packet. So, for example, if you're talking about software routers, then this is basically kind of a norm, because you receive like 10 gigabits or 100 gigabits per second input, and your CPU and your memory bus cannot really handle so many packets and so many decisions, and to forward packet as fast as they're coming in. This is basically creating the problem of head of line blocking. This is similar to TCP, but just a slightly different level, because if your queue is full, you cannot put any new packets, and you basically have to drop them even before you receive the packet. Similar but in slightly different conditions is output port queuing. This is a little bit more common. This is more the one that we look in homeworks. Is basically if your output link is slower than your switching fabric and input speed. So basically, if you have 10 megabit out port and your input speed is like 10 gigabits, obviously you will not be able to send everything that you decided to send on that specific port if somebody is sending a lot of data. One thing that I would like to note, this is not really part of this course, but this is what happens in the real world. For the output port, there is sometimes so-called active queue management. So, for example, instead of just allowing a queue on output port being overflown, and basically you have to drop packets after you decided that you need to forward to a specific port, some routers, and there's a lot of research associated with this, trying to proactively drop packets from the queue, and not necessarily the last packet, but so there's several specific algorithms. So one of them is, if I remember correctly, a random early drop. So basically, a router go over all the output queues, looking if some of them are reasonably big enough, and then just randomly drop packets from that. And apparently, it's actually quite helpful for the TCP, for example, where you don't necessarily drop the acknowledgement, but rather drop random packets from whatever queue you accumulated. One more additional function of the output ports that apply to some of the link layer protocols, specifically to Wi-Fi, is some buffering for the purpose of retransmission. So, for example, when we're using Wi-Fi in unicast mode, then the link layer is trying to ensure that the packet that is being transmitted is being delivered to the other side. So it's basically there's a hop by hop acknowledgement process on each wireless hop. This is slightly different from TCP and the confounded project that you're working with, because it's not done by the end host, but rather the link layer protocol on the wireless link itself. And plus, on top of that, it's not 100% guarantee that this packet will be delivered, but rather it's link layer is trying to achieve some form of reliability with some probability. Basically, it's just trying to retransmit a couple of times and then give up about this packet. But the whole thing about this datagram, about this data, is that it's been kept this in output port buffer. And of course, we still need the line termination hardware in order to connect to the physical layer. A little bit comment that a little bit related to the previous module is how much buffering is actually needed. We talked that in the previous module that we need pipeline from the application perspective in order to fill the whole capacity of the link. And I think we kind of calculated how much of the buffer, how much of the pipeline you need to have in order to fill the pipe. This is similar consideration, but not from the perspective of applications, not from the perspective of the transport layer protocol, but rather from perspective of the network routers. Because network routers technically needs to support all the pipeline that was supplied, like pipeline sizes that's supplied by the applications, and there is a little bit of research that was done to kind of trying to understand how much of the buffer would be needed in typical deployments. And what they kind of trying to give you the formula is about is if you have a link capacity, if you have like estimated round trip time, and this number is basically a rule of thumb, like 250, like assuming that most of the traffic you send in is like across Atlantic, around that number, and you estimated to support n number of flows. So with these considerations, you would get RTT multiplied by the link capacity divided by the square root of number of flows. So this is kind of rule of thumb number that usually being used in the network routers when they deciding how much memory to allocate for the kind of output queues on the routers. In the software, kind of for the software routers, like at our computers, for example, this number can technically be adjusted because you can allocate different amount of memory for the input and output. Like not always, but sometimes you can do this. But for the hardware routers, this is basically a parameter they using or like trying to evaluate when they're creating the router. Because if it's a hardware, you cannot really change anything after you basically build the router. Okay, so that would be it for the summary. What I want you to remember kind of for the network layer protocol, kind of for the basic elements, is that network layer protocol, IPv4, IPv6, it has to be the same for all network entities. So you cannot have like one of the routers speaking IPv4 and others routers speaking IPv6. So basically, we're going to have then, in this case, two separate networks that cannot communicate with each other. In order to communicate, you have to have globally unique IP addresses, like at least they supply for the IP architecture. And in order to have a global unique IP addresses, you need to have some form of organization, some form of a structure that defines how to allocate those IP addresses. And for the actual act of the forwarding, well, the process of the structure of the router, we have the routing process that builds up some information about how to forward the packet, and you can call it a control plane as well. And the forwarding plane or data plane is actual the process of forwarding the packet. And as I show you, this full data plane includes the input ports, output ports, and some form of a logic, how to connect the input port to output port. So like I showed you the three ways of different fabrics to connect, the software-ish, bus, network-like elements. And kind of it's still in all of those cases you're still consulting in some way to the control plane, either directly or indirectly, and we're going to mostly be talking about direct ways of communicating. And kind of after that, the packet you can forward packet on a data plane. Okay, so this is done for the basics, and we're going to have way more complex things in later parts.